PPE, personal protective equipment. Bottom line here, the best way to understand PPE and when you look at it on your different hazards is start either at your feet and work your way up, or start at your head and what? Work your way down and think about how those hazards can affect you. You can start with head protection in the form of what kind of a hard hat can I wear? Most people can get by with a Class A hard hat, unless you're like one of our utility line workers or a high voltage worker where you have a voltage rating that exceeds that, and then you have to go to a Class B hard hat. Primary difference is in the what? The harness that's inside of it and the mil thickness of it and how much protection it affords that person from the force of that voltage that's running through the line. What we don't want to have happen is what we call arc blast occur. That's where electrical energy can voluntarily jump out of the line, hit you, and then proceed through you to ground because it's an easier path. That's where this PPE and those hard hats come into play. Hearing protection. We got another whole slide on it. Now what we're talking about here is what are the action levels and the use of earplugs, the use of what? Muffs, and how we use those, or how we determine whether or not both of these hearing protection modes are required depending upon the decimal output from the surveys that are done in the individual work site because of machine-specific tendencies. Eye protection. What falls up under eye protection? Normally our safety glasses with side shields. I think one of the most dramatic pictures that I've seen about ordinary safety glasses was I saw one that had come back from soldiers that were in Iraq that had been hit by roadside shrapnel, and physical pieces of shrapnel were sticking through their safety glasses that had they not been wearing safety glasses in a combat environment would have taken out their eyes. And perhaps, depending upon where it went, what? Killed them. So eye protection. Goggles over the tops of that, and then of course what? You also get that same visual things from the shields that we use when we're doing some type of ammonia operations, fueling operations, transferring acids or other types of liquid commodities. The next program that we want to talk about is the Respiratory Protection Program. Each company that utilizes chemicals or commodities where potential respiratory problems exist or oxygen deficiencies exist is required to develop a written program. Of all the things that it took OSHA the longest to do was come to an agreement on what constitutes a respirator. The final end product, as stated here, it is a device by which function and design provides the user with a breathable source of air that is free from harmful levels of atmospheric contaminants. Respirators themselves are broken down into two basic categories. They're either air purifying respirators or air supplied respirators. Air purifying respirators, there are four basic types. You can have a half-face respirator, a full-face respirator, a power-assisted purifying respirator, which is a full mask, or you can use the ordinary little paper cloth dust mask like you commonly see them use around sanding type problems. Second category of respirators are what we call air-supplied respirators. Examples of these are self-contained breathing apparatuses, supplied air respirators, or commonly referred to as hose line full-face respirators, supplied air respirator hose lines that have escape bottles, like what we would use in a confined space, so that in the event that the line became contaminated or we had a loss of air pressure, they have a backup means through the escape bottle of breathable air to get out. The fourth kind that you see listed there are what we call down here scape suits, self-contained atmospheric protective ensembles. These are what we use when handling propellants or transferring propellants into our rockets and external fuel cells. It was not until 2 years ago that this particular device was recognized as a respirator. Prior to that, NIOSH wanted nothing to do with that. NASA paid for the entire testing process to ensure that it would become a certified respirator. To that end, how do we know which one of these respirators to select? Because there are so many different ones. The basic answer lies in the oxygen content in the atmosphere that we're going to be working in. The magic number is 19.5. If it's 19.5 or greater, then we know there's sufficient enough oxygen to maintain life. So all we have to do is use an air purifying respirator that can take out any of the contaminants. The other side of that coin is, what do we do when the oxygen content is less than 19.5%? Or that the contaminant that's out there is so lethal that it will not be handled with a filtering system? The answer is, this is when we use air-supplied systems. The air supply systems use at least grade B air, which is then capable of being breathed for a specific period of time without containing any contaminants, and making sure that the oxygen content is sufficient enough to maintain human life. As I stated earlier, in order to put on any of these respirators or use any of these respirators, the three basic criteria have to be met for each one of them. Medical certification, which can cover the whole wide gamut of them as long as they know that you're going to be using them in all roles, training on each of the different types, and then, of course, fit testing on those respirators. Fit testing itself is broken down into two different worlds. We have what we call qualitative and quantitative fit testing. The first one we will review is qualitative fit testing. Qualitative fit testing relies on an individual's subjectivity to a specific irritant, agent, odor, or a taste. Examples: OSHA authorizes the use of saccharin. This is the first element that's supposed to be used. And as long as an individual has a sweet taste in his mouth and he can taste sweet, then you can use this agent. The second agent that's authorized is one called Bitrex. So if it's not sweet and he can't taste something sweet, maybe he can taste something that's sour, Bitrex, bitter. The third one that's used is banana oil, because most of us can recognize the smell of a banana because we've grown up with bananas all of our lives. So once again, if this agent is introduced in the air outside the mask and you can smell it inside the mask, we know that you're able to determine that there's a leak. The fourth agent that's used is isomyl acetate, commonly referred to as irritant smoke by the guys out in the field. What this is that once it's broken, it produces a smoke, and as you introduce that smoke around the sealing surface of the mask, if there's any kind of a leak, they will not be able to stay in that mask. They will come out of it in a military second. The only problem with this is that people sometimes have a tendency to abuse these challenge agents. The sequence in which I introduced them, saccharin, Bitrex, banana oil, and finally irritant smoke, are the protocols that are outlined under the OSHA guideline. Irritant smoke should be the last choice because there have been examples of people that have been gone into respiratory arrest or have induced cardiac problems as a result of the use of this thing, so it should be used very sparingly. The second type of fit testing is called quantitative fit testing. The fit factors developed on how well this mask fits the individual. Samples are drawn from outside in the test bay, which contains an irritant, and then they're drawn inside the mask simultaneously and then run through a computer-based system. There's a laser in there that uses a counter system to count how many particles are being drawn in and how many particles are outside when they're drawn in, and it compares those two values to determine how well the mask fits the individual. Of the two systems, there's absolutely no doubt in anybody's mind quantitative is the preferred method. It cannot be faked, you get a permanent record, and it's totally unbiased. Now that we've discussed the respirators, we've talked about fit testing, the next thing we need to understand is how and when we use them. And what we use is based upon what's called atmospheric composition. What's the air consist of that we're operating these systems in? The atmospheric composition of the air that we're breathing here today is roughly 21% oxygen, 78% nitrogen, and then the remaining 1% makes up all the other gases, the heliums and that are out there. So you can see that it's a fairly significant percentage of oxygen. When we start talking about compositions of that, to convert those percentages into workable, usable measuring tools, what they do is they have an equation called parts per million. To equate 78% nitrogen, this equates to 780,000 parts per million of nitrogen. 21% oxygen, 210,000 parts of oxygen, and then the remaining 10,000 parts to make up the million parts are made up of the various other gases. Next slide. Atmosphere and how that atmosphere affects our ability to breathe is probably one of the most misunderstood parts of respirators. These gases, when we breathe them at sea level, have a specific pressure. And as we raise above sea level, the pressure itself is what drops, not the oxygen contents. All too often, people think that because they go up in an airplane above a certain altitude, that those pilots are wearing oxygen masks because there's not enough oxygen. The oxygen content itself remains the same. It's the pressure that drives the oxygen through the blood vessels so that it can link up with the red blood cells is what changes. So what I'm trying to show you with this slide is, as you can see, there's about half as much pressure being exerted at 10,000 feet as there was when we were at sea level. When you take that on up to 100,000 feet, or at the edge, as you can see, there's very little pressure that's left, less than 10% of the original pressure that there is at sea level. So when they use pressurized systems on board these aircraft, what they're really doing is compensating to allow the oxygen to be pushed through the blood cells. So understanding now the atmospheres that are out there, what are some of the various types of contaminants that can be contained in those atmospheres of air? Well, we have things like gases and vapors, which we can fully understand. But the most of what we have to be concerned with in the industrial sector are what we call aerosols. Aerosols are made up of mists, like when you spray a spray can, fog that can be produced with machines, smoke when we're cutting, fumes which come off of various types of liquids as they off their gases. It's these atmospheric contaminants that we have to be able to select the correct respirator cartridges for to protect ourselves using half-face and full-face air purifying respirators. On this slide, what we see here are marking systems that are used to identify the various types of filters so that we select the correct filter and put it on the half-face or full-face air purifying respirator. The various color codes are used. Black for organic vapor is one of the most common. Acids are when you're working around acid-type gases, white filters. But all too often what they will do is they will combine filters into what we call a combination filter, and they'll use the yellow markings on it so that we can identify that it does both organic vapor as well as gas. Other ones that are quite common, ammonia with green, and of course mercury vapors, or when you're doing a mercury spill cleanup, we would use an orange colored filter. Now that we've discussed the different types of filters, we need to understand how they function. How filters function and whether or not how efficient they are will be decided on by a series of codes called N, R, and P. The letter N that precedes the percentage of success that that element has indicates that it cannot be used with oils. It's non-oil protected. R means that it is resistant to oil, and P means that it's oil proof. And obviously, the oil-proof cartridges are going to cost a lot more than the ones that are resistant or the ones that are non-resistant at all. And so the applications will be changed. The other numbers that you see listed there, 95, 99, and 100%, are numbers that you normally find behind that letter code. For example, an N95 filter. An N95 filter means that it's not oil-proof, and it will stop 95% of all the contaminants that are drawn through it. An R99 filter means that it is resistant to oil, and it will stop 99% of all the contaminants that came through it. A P100 filter means that it is a oil-proof filter that will stop 100% of all contaminants that come through it. That's the way it's advertised, but honestly, there's no such thing as totally oil-proof. They're probably closer to 99.99% would be a better estimation. The last thing that we see on this slide down there is that nice little round circle. It's supposed to be the color pink, and what this indicates is what we call a HEPA filter. HEPA filters are used against these dust particles that we talk about. It's used against asbestos. And what it is it's a very fine mesh screen that limits the size of that particle coming through and stops it. Hand protection occurs primarily through the use of gloves. When we start dealing with gloves, we need to understand that this is where the properties of the commodities come to bear. The main things that we're concerned about with gloves is absorption. If you're handling chemicals, you don't want to use leather gloves. You don't want to use cloth gloves because these things will absorb those chemicals and allow them to come in contact with our skin. This is where those polypropylene gloves come into play. If you're handling sharp objects, they have metal mesh gloves that are used to keep you from cutting yourself. Or once again, you can use leather gloves. So the hand hazard has to be matched to the type of glove that's worn. You can't just assume that one glove will do it all, and that's a leather glove, because leather gloves will not work against the chemicals. Foot protection. Foot protection is another one of those things that's often overlooked, especially guys that do a lot of climbing on ladders or spend a lot of time on scaffolds or that. Your footwear when you're climbing fixed ladders. You have to be making sure that that footwear has a capability of having a heel to keep you from sliding through or off the rungs of a ladder. Because when you mix a little oil with a little bit of moisture or morning dew on one of those ladders or scaffolds, you can slide through that ladder and wrench or twist your knee and find yourself taking a serious fall. Other things that come into play are steel toes. Steel toes are used to protect the foot from being crushed. Other types of things are shanks that they put in boots that keep the foot in a horizontal plane so that it does not bend around the rung of a ladder, causing it to develop an ergonomic type injury from constantly being bent and destroy the arches or something like that in the foot. So these are all forms of PPE. As you enter into this world and as you enter into the various processes in aerospace tech, you'll be required to wear specific PPE equipment. Just remember that the specifics of that equipment are found on your MSDS sheets. If it calls for it, wear it. If it's called for it and you're not wearing it and you get hurt, then you put your livelihood at risk, as well as perhaps your family. Next area that we want to talk a little bit about is hearing conservation. Hearing conservation in the past 3 years has become a significant item from the Secretary of Labor. The problem is that our workforce is being exposed to a lot of deafening noise in the workplace. Under the standards that are written, we have some specific rights. We have the ability to require our employers to do what we call noise hazard assessments. They bring in specific audiometric testing equipment and determine what is the average frequency of the noise that we're being exposed to. Then, if this noise hazard exceeds the permissible levels, they're required to post noise hazard signs. Normally those are yellow signs and they've got a pair of black earmuffs on them so that when you go to enter into a shop or into an area that requires hearing protection, you recognize that sign and you don your hearing protection before you open the door and are exposed. Under the federal standards, any employee who's exposed to noises that exceed 80 decibels is required to wear hearing protection. That's straightforward. That is what we call the action level. Coming down from there, 85 decibels. At 85 decibels, if you are exposed to a noise hazard of 85 decibels or greater for a period of 8 hours, then they're required to enroll you into a hearing conservation program. This hearing conservation program will then do a baseline test on you as part of your hiring process, and then every year they're required to do a follow-on audiometric test on your ears. What they're looking for there is what we call hearing shift to occur. And any time you have more than a 10 decibel shift in any of the frequency zones, now that becomes a reportable OSHA injury, just like breaking a leg or losing a finger in a bandsaw. It's a reportable OSHA accident. This is what's driven the standard, and this is the game that they're playing now in order to reduce the amount of injuries that take place in the workplace. 90 decibels is what they call the OSHA permissible exposure limit. Any person who's exposed to 90 decibels or above, just exposed to them, will incur a hearing loss associated with it. And at no time when the hearing noise outside is at 115 or greater, it cannot be exceeded. That is the maximum that anybody can be exposed, is 115 decibels. Noises that are greater than 115 decibels require hearing protection to reduce that down to the effective hearing range that's underneath that permissible exposure limit. So how do we protect our ears? The answer to that is really two worlds. We can either use earplugs or we can use earmuffs. Earplugs themselves are broken down into two categories. So we've got what we call disposable ones. Those are the ones that we kind of roll up, put in our ears, and when we're done, we take them out and we throw them away. Normally they look like just a little cylinder of foam. Then we also have what we call reusable ones, which means when they're issued to us, it's our responsibility to take care of them and wash them and clean them after each use, put them back in an approved container, and then the next time we need them, we've got them with us already. Usually of the two, they both function equally well, and I will admit that most people are moving more and more towards the disposable world. The rationale there is not that they're better. The rationale there is that the average worker sometimes just doesn't practice hygiene the way he should, and if you don't wash them and you just put them in a container, it can cause ear infections and cause other hearing loss problems other than just exposure. To that end, what I remind you of is to check those hearing containers or those packages that contain those earplugs that you're offered. On there, you're going to see something called an NRR. This is what we call a noise reduction rating. Normally with disposable earplugs or reusable earplugs, you'll find that that's normally between 28 and 33 decibels. People say, well, why is there such a difference in them? And the answer to that lies in the material that they're made out of and how well, when they expand and are inserted into the ear, do they seal the ear canal. Whether they're single flange or triple flange plugs will make all the difference in the world. Earmuffs, on the other hand, are a little more simple. They simply go on over the top, much like the headphones that we wear with our iPods today or with some type of stereo system that you may have or own. These earmuff systems function the same way. But then they also are only as effective as how well they fit, how tight they are. Individual hair structures, when they got long hair that's blocking that surface. Sideburns that could affect how well it seals. So anyway, the noise reduction capability of earmuffs themselves are anywhere from 25 to 29 decibels. Anytime that we have an outside noise factor of 100 decibels or greater, OSHA requires the use of double hearing protection. That means we have to wear the earplugs inside and the earmuffs over. The effectiveness of that particular combination will be predicated off of how tight that set of headphones tighten down on our face, as well as how well the earplugs are positioned into our ears. To determine what is commonly referred to as the working protection factor of that earmuff system, what we need to do is take the NRR rating for each of those systems, subtract 7 decibels from it, and then divide by 2. So let's say effectively if it had an NRR rating of 70 and we had to deduct 7, that would take it to 63. Divide that by 2 would give us 31.5, which we would use 31 decibels. So then we could take that 31 decibel working protection factor, subtract it from the outside noise to get us down into the protection zones that are required by federal law.